talked about adding and subtracting our radicals, right? And we said that the rules for our radicals when adding and subtracting were just like they are for your variables, right? We said we treat them the same way. So, quick reminder, when I have like variables, like here it says 3x plus 2x, we were allowed to add those, right? And we get 5x, right? Which meant if we had 3 root 5 plus 2 root 5, we were allowed to add that as well, right? Because they match. And that gave us, nice. Okay. What about if we had something like 3x plus 2y? Are we allowed to add that together?
No.
No. So was I allowed to add 3 root 5 plus 2 root 3?
No.
Right, because they don't match. Okay, so when adding and subtracting, they have to match if we're going to add them, right? Okay. So now today we're going to talk about multiplication and division. Still true, we treat them like our variables. So first, let's look at some variables. 3x times 2x, what is that? 6x squared. All right, so we multiplied the coefficients, right? 3 times 2 was 6, right? And then x times x is what gave us the x squared. Because when we multiply variables, what do we do with the exponents? We add them, right? There's an understood exponent of 1 and 1, right? 1 plus 1 is what gave us the 2. Okay. The rule will be the same when we're multiplying our radicals. So here, we said to get this 6, we multiplied the coefficient 3 and 2, right? So I need to also multiply the coefficients here. 3 times 2 is going to give us 6. Okay? And my radicals match, so something special should happen, kind of like over here where we were able to add the exponents, okay? So what is square root of 3 times square root of 3?
3 squared. That's 3.
Just 3. Why is it just 3?
It's half of itself, or like.
Right. Somebody said whatever it's the square root of, right? So 3 times 3 would be 9, right? So it would have been square root of 9, but the square root of 9 is just 3. Okay. So that's what the special thing is if the square roots are the same number underneath them, then it should just be that number without a square root, okay? So square root of 3 times square root of 3 is 3. Square root of 5 times square root of 5 is 5. Square root of 173 times square root of 173 should just be 173, okay? Now, these are both regular numbers, so I could multiply them together to simplify a little further. We get 18, okay? All right, what about right here? We've got 3x times 2y. What is 3x times 2y?
3x 2y. 3x 2y.
6xy, there we go. Okay, so what we did here was, again, we multiplied the coefficients, right? 3 times 2 is 6, but my variables weren't the same like last time, right? So I couldn't add the exponents together. I had 1x and I had 1y. So I put an x and a y, okay? All right, so same thing over here. I look at my coefficients. 3 and 2, what is 3 times 2? 6, okay? My radicals don't match, so it's not going to be like last time where the square root just goes away. I need to actually multiply the numbers and see what I get. So what is square root of 5 times square root of 3? Square root of 15, okay? Well, is there anything that multiplies to give you 15 and has a square root? But if there was, we would simplify, okay? All right, so now that we kind of have an understanding of what we're supposed to be doing, let's try some examples of multiplying. So on number 1, if I were to multiply, what is square root of 2 times square root of 8? Square root of 16. Very good. After we multiply, it says, then simplify, which would just be perfect. Okay. On number 2, again, I'm going to multiply. Remember, we multiply the coefficients, so the things in front of the square roots, and then we multiply the things under the square roots. There's an understood 1 right here, right? So I multiply this 1 and this negative 2, which would give us, good. And then I multiply the stuff underneath. 3 times 27. What is 3 times 27? 81. So square root of 81. All right, so we multiplied. Now we're supposed to simplify. Can we simplify? Yeah, square root of 81 is, right. So I got negative 2 times 9, or negative 18. Nice. Okay. All right, same idea for number 3. Multiply the coefficients, multiply the radicals. So what am I going to get when I multiply? 12 square root of 12. Very good. 4 times 3 gave us 12 on the outside. 6 times 2 gave us 12 on the inside. Okay, but can we simplify?
Yes.
Yeah, what multiplies to give us 12 and has a square root? 4. So I'm going to rewrite this as 12 times the square root of 4 times the square root of 3, right? And what is the square root of 4? 2. And there was already a 12 out here, right? So it'll be 12 times 2 square root of 3, or 24 square root of 3. Very good. All right. On number 4, what property am I going to be using? Distributive property, right. So I got 3 times 1, which is 3. And then I also multiply that 3 times negative square root of 2. So remember, there's an understood 1 right there, right? So what is it going to be?
Negative 2.
Perfect. Okay. Now we would love to subtract, but our rules for addition and subtraction say if we're going to do that, then the radicals have to be the same. Do those two pieces have the same radical? So that's where I have to leave it. Okay. All right, what about number 5? What would I get if I multiplied these two radicals together? Good. Square root of 256. And will that simplify? Nice. Square root of 256 is 16. All right, and then number 6, not only do they have some numbers, they also threw in some variables. So, underneath the radical, what is 40 times 8 going to give us? 320. And then when I multiply y squared times y to the 5th, you guys said we do what with the exponents? So that'll be good. All right, and then we try and simplify, right? So there's probably not a perfect square root for 320, but we want to try and think of some numbers that multiply to give us 320 that do have a square root, preferably the biggest one. 64 and 5, good. So this is going to be square root of 64 times square root of 5, and then we also still have that y to the 7th under there. All right. So the square root of 64 is 8. But there is no square root of 5, right? So this is going to stay a 5 under here. Okay? And then we went over how we simplify radicals last week. So depends on if the exponent's even or odd. Ours is odd. So what do we have to do? Subtract 1, which gives us 6, and then divide by 2. So I get to take out y to the 3rd. But that 1 that we subtracted is still in here, right? Okay, good deal. All right, you guys try numbers 7 and 8, and then we're going to share what we come up with.
We're just so signal. We also Seven times 42 is 42. I said 294. And the square root is 7. 294 divided by 49.
So how we're going to do this? Yeah, I have no idea. Very complicated.
Wait, 249?
We have x times the square root of x on top.
Divided by
And on bottom, we have whatever. So you multiply 5x. Why? Where is the number back?
no, it's 7.
It's the exact same.
49.
5x, y on bottom.
294 divided by 49.
Oh, yeah. Is that times 5x
6 should be
squared
on
y.
the side.
So then results in square times, it's like 42 or 5y over 5xy, which would then result in x times 5y.
Oh, yeah, 49
All right, looks like most of you guys have that. So let's take a look at number 7. So on number 7, what did we get when we multiplied, first of all?
294.
Okay. 294. What?
X cubed y to the power 9.
Very good. Everybody good there? Okay. So from here, I then was going to try and simplify, right? So I'm trying to think of some numbers that multiply to give me 294, one of which that has a square root, right? If you don't know and you're having trouble trying to figure it out, pick some numbers that you know do have a square root, right? Like 25, 36, 49. Try those out first because that's what we're looking for anyway, right? So what ended up working here?
49.
Good. So 49 times 6. All right. And the square root of 49 was 7. Okay. What did we do about the x cubed and the y to the 9th?
Okay, so it's 7x.
Okay, so we put what on the outside?
X squared and y forward.
X. Just x, right?
X, and then y to the power 4.
And then y to the power of 4.
And then you can just
Okay. And then since they were both odd, they both have 1 on the inside, right? Okay. So remember, guys, the rule is -1, then divide by 2, right? So 3 minus 1 is 2. 2 divided by 2 is 1. So that's why I took out 1. 9 minus 1 is 8. 8 divided by 2 is 4. So that's why we took out the 4. Okay. All right, for number 8. On number 8, what property did you have to use? Distributive property. Good. So when we distribute, what was square root of 2 times square root of 50? Square root of 100. Okay. And then what was square root of 2 times -7?
-7
All right. And then we wanted to simplify, right? What simplifies here? But can we actually subtract them? No, because they don't match. So we leave it there. All right. Okay, so when you multiply, like you probably already saw, that's why those questions were on the back of your 1.2 assignment. We were practicing multiplying normal variables so that when we get here with a radical, we know what to do. Okay? All right. Okay, flip it over on the back. Okay? And we're going to go over the rules for division real quick. So for division, remember, we're not allowed to have what in the bottom of a fraction? 0. We can't have 0 in the bottom of a fraction. Okay, so that's what they remind us of here. They also say you are allowed to rewrite the radicals interchangeably, like this and like this. So you could have it written as 2 separate square roots over one another, or as a single fraction under one big square root. They mean the same thing, okay? The reason we might want to have it written one specific way is because sometimes it's easier to simplify in the specific form, okay? So, on number 1, you notice they wrote it as one big square root, right? That's so, if possible, I could simplify this. Well, does 243 over 27 simplify?
Yes.
To what?
9.
Which is a lot nicer. And then the square root of 9 is just 3. So prime example of why we might like to write it as one big square root. Okay, number 2, they didn't do that, but should it maybe have been written that way? Can we divide 81 by 3? Yeah. So I'm going to rewrite it as one big square root, kind of like number 1 was. And I already heard somebody say you get what when you divide? 27. Okay. On the front, you guys told me when I multiply, I add my exponents. So what do I do when I divide? Subtract. Perfect. All right, and then that's something that simplifies, right? What does 27 simplify to? 9 and 3. So 3 square root of 3. And what about that x to the 4th? X squared. Good job. All right. On number 3, does that one simplify?
Yeah.
Yeah, what do we get when we divide those? 256. All right, and what do we do with the exponents? Subtract, so I get x to the 5th. And then we simplify.
16.
So 16, And what about the x to the 5th?
X squared.
Uh-huh.
Root X.
Nice. Because it was odd, there's that 1 left over inside. Okay. All right, the only other rule that's important whenever you're dividing is something that we call rationalizing the denominator. If you've already taken geometry, I know you did a lot of this when you were doing your special right triangles, but rationalizing the denominator just means we are not going to leave a square root in the bottom of a fraction, okay? So let's do one of these real quick before we have to go. On number 4, they wrote it as 2 separate square roots, right? Because it's not beneficial for it to be 5 over 3. 5 doesn't divide by 3, right? So we want to leave it this way, but I'm not allowed to leave a square root in the bottom. Well, on the front, we said square root of 3 times square root of 3 was just what? 3. Well, if I'm trying to get rid of a square root, that would be ideal here. So I multiply it times itself. Because like you guys just said, that's going to make the square root go away, right? But rules say if I do something to the bottom of a fraction, do it to the top as well. Okay? So in the numerator, I have square root of 5 times square root of 3, which would be square root of 15, over square root of 3 times square root of 3, which is 3. All right? And now there's not a radical in the denominator, so I would be good to go. Okay? All right, we're gonna finish these up tomorrow, so make sure you bring them back with you. Again, 1.2 due at start of class, so make sure that's finished. So I is square root of -1. I squared would be just -1. When you square it, the square root goes away.
We didn't, but their teacher was I know Parker Allen.
How do you do conjugates?
We will get to that tomorrow.
I honestly do not.
I'm the shooting girl.
Get the square root out of it. Because you multiply by the square root of 3.
He turns around when like Jake.
And then you have square root of 3 on the other side of that
Then as soon as
binomial.
I go to shoot, he turns around
So
and I
when
hit a
you
banger
multiply
top
the
corner.
conjugate, you don't just multiply by square root of 3.
Jake and
Okay.
Nate will shake their shots.
It's like it's square root of 3 and the 1.
Huh. And the 1, yes.
Which I simplified to get the reciprocal of that, which doesn't make sense.
Andrew was hitting bangers.
Numbers.
I was hitting the opposite of bangers. I hit one good shot. It was top shot.
Bye. You too. So for number 5, since this is written as a single fraction, we can simplify 12 over 14 to 6 over 7. So we have the square root of 6 over 7, but we're unable to simplify further, so this would be when we would like to rewrite it as the 2 separate radicals. Again, we don't leave a radical in the denominator, so I have to multiply top and bottom by square root of 7, which would give us square root of 42 over 7. And square root of 42 does not simplify, so we leave it just like that. On number 6, this one would simplify a little bit as well. This x and an x from up here can divide out, leaving us with square root of x squared over square root of 5y. Now up here, the square root of x squared would just be x over the square root of 5y. Again, we have to rationalize the denominator, so we multiply the denominator times itself. So up here in the numerator, I'm going to have x times the square root of 5y all over 5y. For number 7, this one also cannot be simplified, so I'm simply going to rationalize the denominator. But remember, that means we're multiplying everything in the numerator by square root of 5. So 3 times square root of 5 would be 3 square root of 5 plus square root of 5 times square root of 5 is just 5 over square root of 5 times square root of 5, which again is just 5. All right, so next we're going to talk about multiplying by the conjugate. First, we're going to define what a conjugate is. This is going to be a pair of expressions that results from changing the sign in a binomial. All right, so on number 8, if I am going to multiply by the conjugate, then in the denominator, I multiply by itself, but like it says, I'm going to change the sign of that binomial. So instead of multiplying by 1 plus square root of 3, I'm going to multiply by 1 minus square root of 3. But if we do that in the denominator, we know we must also do it in the numerator. So now we're going to multiply that out. So in the numerator, I'm going to have 2 times 1, which is 2, and 2 times negative root 3, which would be negative 2 root 3. Okay? And then when we multiply in the denominator, you will see why we multiply by the conjugate instead of by the exact same denominator. So we're going to have 1 times 1, which is just 1, and then 1 times negative root 3, which is negative root 3, and then root 3 times positive 1, which is positive root 3, and positive root 3 times negative root 3, which would just be negative root 3. So in the numerator, we've got 2 minus 2 root 3. Over here, we've got a negative root 3 and a positive root 3, which would give us 0. And then I've got 1 and negative 3, which are like terms that I can combine. So this would just give me negative 2. Now both this term and this term are divisible by 2, so I'm going to divide both by negative 2. So 2 divided by negative 2 would be negative 1, and negative 2 divided by negative 2 would be positive 1 root 3, or just root 3. All right, let's do another one of those. So for number 9, I multiply both numerator and denominator by the conjugate. So this time I'm going to multiply by 3 plus square root of 2 in both the top and the bottom. So here I'm going to have square root of 2 times 3, which would be 3 root 2, and square root of 2 times square root of 2, which is just 2, over that denominator. So I'm going to have 3 times 3, which is 9, 3 times square root of 2, which would be positive 3 square root of 2, negative square root of 2 times 3, which is negative 3 square root of 2, and negative square root of 2 times positive square root of 2, which would just be negative 2. Well, again, these two are going to go away, and these two are like terms, so I can combine them. So I'm going to have 3 square root of 2 plus 2 in the numerator over 9 minus 2, or 7 in the denominator. This time, my numerator is not divisible by that denominator of 7, so I leave it right there. All right. And then we got one more like that. So I multiply top and bottom by the conjugate, which in this case is going to be 4 plus square root of 3 in both the top and the bottom. So here I'm going to have 4 times square root of 5, which would be 4 root 5, and then root 5 times root 3, so plus root 15, over, in the denominator, I'm going to have 4 times 4, 4 times root 3, negative root 3 times 4, and negative root 3 times positive root 3, which is negative 3. So these would go away, and then I can combine 16 and negative 3. So I'm left with 4 root 5 plus root 15 all over 16 minus 3, which is 13. Again, not divisible, so that's where I leave it. All right, and then the last thing we're going to look at is complex conjugates. So this is going to be a complex number times its conjugate always results in a real number. Which would be ideal for us. So on number 11, again, I'm going to multiply by the conjugate. So my conjugate here would be 5 minus 6i in both top and bottom. So in the numerator, I got 4 times 5, which is 20, and 4 times negative 6i, which is negative 24i. In the denominator, we got 5 times 5, which is 25, 5 times negative 6i, which is negative 30i, and then 6i times 5 would be positive 30i, and then 6i times negative 6i, which would be negative 36i squared. Okay, so then I simplify. In the numerator, there's not necessarily anything that I can combine. But if I do look at those terms, I could pull out a 4 if I'm trying to see if there's anything I could divide out later. So I could write it as 4 times 5 minus 6i. In the denominator, my negative 30i and positive 30i will go away. And then like on our 1.2 assignment, remember we know that I is equivalent to square root of negative 1. Therefore, I squared would just be negative 1. So this would be negative 36 times negative 1, which would actually be positive 36. And positive 36 and 25 are like terms, so I could add those together and I would get 61. Now 4 and 61 not divisible, so I'm going to leave it just like that. All right, for number 12, same idea. I'm going to multiply by the conjugate, so this will be 1 plus 3i. So in the numerator, 2i times 1 is 2i. 2i times 3i would be 6i squared over the denominator, which is going to be 1 times 1 plus 1 times 3i. And then we would have negative 3i, and lastly, negative 9i squared. Okay, so positive 3i and negative 3i, those go away. Anywhere I see an I squared, we know that we can go replace it with negative 1. So I would have 2i plus 6 times negative 1, which would just be negative 6, over, in the denominator I've got 1, and then here we had negative 9 times negative 1, which would just be positive 9, and 1 plus 9 is going to be 10. Now in this case, all of my numbers here, 2, 6, 10, those are all divisible by 2, so I can simplify a little bit. So 2 divided by 2 would just leave me with I, minus 6 divided by 2 is 3, over 10 divided by 2 is 5. Oops. All right. Okay. And then last one, again, we are going to multiply by that conjugate, which in this case is going to be 3 plus 2i. All right, so in the numerator, I got 4 times 3, and I got 4 times 2i, and I got I times 3, and I times 2i. All over that denominator, which is going to be 9 plus 6i minus 6i minus 4i squared. So our positive and negative 6i in the denominator will go away. I'm going to combine like terms in the numerator, also reminding myself anywhere there's an I squared, like here and here, that I can replace that with negative 1. So in the numerator, we had 12, and then we had 8i and 3i, which would combine to give us 11i. And then I would have 2 times negative 1, which would be negative 2. Over in the denominator, we have 9, and then we were left with negative 4 times negative 1, which would be positive 4. So we end up with, 12 minus 2, which is 10, plus 11i, over 9 plus 4, which is 13.